Today, we're going to learn about acids and bases, folks. Acids and bases. They're everywhere. Acids can melt your face. Bases can melt your face in completely opposite ways. In some ways, they're the same. In some ways, they're different. In some ways, they're opposites. It's all just confusing. Well, let's talk about them. Acids, things that are acidic. Citrus fruits, they contain citric acid. They taste really sour, like you bite into a lemon. That's what an acid would taste like. Feel free to do so right now. Bases, they taste bitter. In order to taste what a soap is usually basic, if you ever want to taste what a base tastes like, bite into a piece of soap, go for it now. Thank you. Both acids and bases are electrolytic, meaning they break apart into ions when placed in solution, and thus allow the solution to conduct electricity like we learned in the last unit. Acids, the most common acid we usually work with is hydrochloric acid, breaks apart into H+ and Cl-. And then acids are kind of funny because this is a relatively unstable solution. Usually what's going to happen is it's going to get picked up by a molecule of water. So your H+ is going to join in with a water molecule to form something called a hydronium ion. So you can see acid solutions represented, or acid particles represented as either H3O+, the hydronium ion, or H+, which is just the hydrogen ion. Pretty much look at those interchangeably. Bases, on the other hand, the most common base we work with is sodium hydroxide, and that's a strong base, and we'll learn what that means in the next video. Breaks apart into sodium ion and the hydroxide ion. All right? Now, acids and bases are opposite because they can both neutralize each other. Because since acids contribute H+ to a solution, and bases contribute hydroxide to the solution, when those two things combine, what you end up with is water, a nice neutral compound giving a pH of 7. In another video, we'll also get into the pH scale in much more detail, but for now what you need to know is that water has a pH of 7. Anything less than 7 is considered to be acidic. Anything over 7 is considered to be basic. Now, there are additional definitions for acids and bases other than just H+ and OH-. That's the most basic definition, the Arrhenius definition, where acid is an H+ donor and bases are hydroxide donors. However, not all bases contain hydroxide. A common base that we use all the time for cleaning is ammonia. And even though ammonia itself, NH3, does not contain a hydroxide, it is capable of accepting a hydrogen ion from water and then producing hydroxide ion in solution. So the definition has to be expanded a little bit more than just hydroxide donor. Now it's a H+ acceptor as the Bronsted-Lowry. And then even further, there are a lot of them that don't necessarily do just this or interact exclusively with water, but they're capable of donating their electron pair to another atom that has some slightly positive region. Now we're going to talk about the difference between strong acids and weak acids, and water. Water itself, which is H2O, as you all know, self-ionizes at a very low concentration, 10 to the -7th molar. And we'll get into that in a lot more detail when we talk about the pH scale. But for now, you can assume that if you have water, there's a very tiny amount of hydroxide ions floating around and a tiny amount of hydronium ions floating around. Let's just the pH of 7. If we're looking at a strong acid, you can see that it dissociates completely. A represents the conjugate base of the acid, and we'll get to that in another video as well. But basically it dissociates to produce hydronium ions, or H+ ions, and then the remainder will be left behind, completely separated. Notice that it has a pH of 2, which is relatively acidic at that concentration. At the same concentration, a weak acid would produce a much higher pH because only a small portion of the acid molecules would dissociate. So you can see that all of these gray here represent the acid molecules that haven't dissociated, and only the colored ones are the ones that dissociated. So you see it's a low concentration of those. Similarly with bases, a strong base, rather, is going to contribute, it's going to break apart entirely. You're going to have some metallic ion or cation, and then the hydroxide being produced, and all of the ions will separate when placed in solution. Some weak bases, however, the ions are held together more strongly and they don't dissociate completely in solution, and you end up with a much lower concentration of hydroxide ion in solution. Thus, it would have a lower pH than a strong base. Now, just to show you that both of these are electrolytic, if you have, right now we're comparing, this lighting up because it can complete a circuit. This is a weak base. It dissociates partially. If you compare that with a strong base, you can see that the light bulb is quite more intense. So weak bases are weak electrolytes, strong bases are strong electrolytes, and it's the same thing for acids, where a strong acid will be a strong electrolyte, conducting electricity really well, and a weak acid will do it a little bit. One last thing, usually we say acids turn litmus paper red. We don't always use litmus paper, we usually use pH paper or a pH meter, but you can see that the color of this paper will indicate what pH it is. That's about it.